Okay, so here's where we were last time. We were talking about multivariable functions and how they're different from single variable functions. The point of view that I like, and I encourage you to take, is that they are functions that where the input, instead of being a number, the input is a vector living inside of Rn. And you can think of course, as a bunch of variables, right? A vector is defined by a bunch of coordinates, which you can think of as a bunch of variables. But honestly, it ends up being really more valuable to think of it this way. Think of the input as a vector. And then likewise, what comes out might be a vector. Right? Again, you could think of it as a bunch of variables, but it tends to be more valuable to think of it this way. Okay, so we talked about about notation and terminology. I won't repeat that again. But I want to move on now to some examples. This first one is intended to just be relatable, but the weather, right? Standard water cooler conversation, right? The most trivial of conversations. If you think about it, you're actually talking about a multivariable function. We don't think about it in those terms at the water cooler. But what you're telling me is you want to talk about temperature. Well, that depends on where you are and when you're talking about. Right? Temperature now, at this point, is not the same as the temperature 5 hours from now. The weather also includes barometric pressure. That also depends on where and when you're talking about. Humidity depends on where and when you're talking about. So now that's just a couple of really well-known, trivial, easy, rattle off the top of your head weather variables. You could imagine more characteristics of weather that depend on where and when you're talking about. And so what we have here is a highly multivariable function. There are 3 input variables. Right? And you give me values of these 3 input variables, and I can correspondingly tell you the values of these, just the 3 here that I've enumerated, output variables. Okay, so I think that's an eyebrow raiser. That's something this mundane, right? We're actually doing multivariable math there. Okay. Something that's maybe a little less trivial, but maybe more persuasively important. Here's an example from business. If you're running a business, or if you have certain things under your control in whatever context, naturally you're going to be interested in how much risk is associated with choices that you might make about variables that you have under your control. So maybe, again, if you're a business owner, you can control. And by the way, side note, full confession, I don't really know any economics, right? But this is just intended to be, you can see how such an example would clearly exist. Capital is something you might have control over, right? Labor, how many people do you hire in your small business, what have you? Interest rates are going to affect things, right? So several input variables affect risk, which is therefore a function of those input variables. Likewise, you'd like to know your expected profit, right? I mean, you better care about your expected profit if you want to stay in business, right? And those also might depend on some of these input variables. So again, this is just a superficial example, but you can well imagine that in a business there's more than 3 variables. Right? Labor, for example, maybe instead of just how many people do you hire, there might be several variables related to labor. How much, how many people do you hire with a certain skill set? How many people do you hire with a different skill set, etc.? Maybe there's several different kinds of employees, several categories of positions you need to fill. You can easily see a simple matter of what should I do with my business? Multivariable function. Right? Okay. All right. So I like to throw a couple of examples out there just to persuade you that you should care about this. This, multivariable calculus isn't just, curious ramblings of obscure ivory tower mathematicians, right? This is very real world relevant topic. Okay. Let's talk about how would we draw pictures of such functions. Right? Now, graphs are the answer to that question in single variable calculus. Almost always. If we're talking about the kind of function you would see in a single variable calculus class, you've got an input variable and an output variable. That's it, right? One variable in, one variable out. And typically we write this down. We write y equals f of x. We call it the graph. We draw pictures. They're so ubiquitous in single variable calculus classes, we don't even really think about that as being a choice. That's just what you do. That's what the function is. And it's important going forward here in a multivariable calculus class to realize that's not true. A graph is not just what a function is. Drawing pictures in that way is not just what you do. It's a choice. It's one way to look at a function. And very often, not even a very good one in a multivariable context. I'm going to, for the rest of this talk today, I'm going to be talking about that kind of thing. So first let's talk about what is a graph in a multivariable context. So I'm going to give you a general description first. Let's talk about if you have a function where maybe you write y equals f of x. Let me first point out what you have here in this function is you have a function f with n input variables and one output variable. Right now you can explicitly see this input is a vector that's coming out of, I'm going to say, Rn. Right? And you can explicitly see that the output, well, I just gave, this example has just a single output variable. So the output is a value in R1. So this is a function. This f is a function from Rn to R1. Okay. And the way we're going to form the graph, and this is just a rip-off, straight-up rip-off of how we do it in single variable calculus. Right? The graph is going to be the set of all points that take this form. Notice it's I'm going to loosely say x comma y. I mean, it's just like we did in single variable calculus. It's just that, okay, well, these the first several coordinates are now the input variables, plural, right? Because we have vector valued input here. But then there is also, right here in this same list of coordinates, we're attaching also the output value, the output variable, which of course is just the value of the function, which is this in this output space, the target, R1. Okay. So first thing I want to point out about graphs with this construction being made is that they are what I'm going to call dimensionally weird. You would kind of think if you've got a function with n input variables, I mean, students kind of reflexively think, okay, well, the graph is, I mean, look, we've got a function on Rn, so the graph is in Rn, and it's not. It's in, if you think about it, it's in Rn plus 1, because check it out, we've got n coordinates that come from the input, but we also have another, in this case, 1 coordinate that comes from the output, and all together then, grand total, we have n plus 1 variables, right? So this is weird. The graph does not live in the domain. It does not live in the target. It lives in a brand new hybrid kind of vector space that we made up explicitly for the purpose of giving the graph somewhere to live. It's weird. It's arbitrary. Side note, let's talk about single variable calculus again. Did you ever think it was weird in doing single variable calculus that you were making 2-dimensional pictures and there were clearly 2 variables, x and y, right? So, okay, well, I mean, that's the weirdness of the graph construction. The graph construction takes a single variable function and it makes a 2-dimensional picture out of it. So anyway, it is what it is. Just wanted to point that out. Now, let's have a slightly more relatable example. Let's get a picture on the page. It's very satisfying. Let's consider this function here. This function, I'm going to say this is f from R2 to R1. Notice, because the domain Well, the inputs have 2 coordinates, which means they're vectors in R2. The output has, just 1 coordinate, so it's a vector, if you will, in R1. So function from R2 to R1. Following the pattern, we notice that the graph is the collection of all points with coordinates like this. Write down the input coordinates and the corresponding output coordinate as coordinates of a single point. Okay? And think about the fact that we'll look for every input point for every x1 comma x2, and I'm going to sloppily, forgive me for this, draw it as if it's sort of down there. Kind of. I mean, this is kind of sort of R2. It's not exactly, but for every input point, there is a corresponding output value that tells you how far to go up, right? Thus resulting in a point on the graph. So I appeal to your geometric intuition. Every point, if you will, down here in the plane is going to get shoved up by some amount to give you a point on the graph. And seems plausible to expect that most of the time, the kinds of functions we're going to be dealing with, you would expect then the graph would be a surface. Yeah? What do you think? Everybody happy with that? Okay. All right. Okay. All right. So, fine. Let me start with the good news. The graph construction, this kind of thing, is very useful. Often, maybe even I'll say. Certainly sometimes, but maybe I'll even say often. I do want to point out, though, it is highly flawed. This has got lots of shortcomings, and it's really easy to point to the big shortcoming. Okay, how would I draw graphs of these highly relatable, clearly important functions? And remember the counting that we did of how many variables there are involved. Let's take this business function right here, for example. Well, we've got 1, 2, 3 input variables, and then another 2, making a total of 5 once you include the output variables. The graph of a function like this is going to be a picture that lives in R5. Right? I mean, you can't even pretend to be able to draw such a thing. And I don't really believe anyone that says that they can see it in their minds. That, I don't buy it. I certainly can't. Right? At a minimum, it's extremely hard. But you definitely can't draw it. So this is one of the really unfortunate things about the graph construction. It just doesn't work. Extremely often in a multivariable context, you just can't draw it. Right. So let me show you another, and likewise in this case up here, for example, here where I have 6 variables, and again, out of the question. Right. So let me show you a different way that you can visualize these multivariable functions, if need be. And this is so very importantly, the picture I'm about to draw now is not a graph. This is going to be a qualitatively, fundamentally different kind of a picture that will nevertheless represent a function. It's not a graph. So here I go. This function here, this g function that I've got down here, is a function from R3 to R2. And I'm just going to draw the domain. And then I'm going to draw the target, and I'm going to draw maybe a couple of examples of points that are over here, kind of landing over here somewhere. This is a very simple-minded, sort of obvious way to draw such a thing, but we'll start with the domain, R3. Here's my picture of R3. Right, maybe the axes are the K, L, and I axes. An input to this function is, I can visualize it as being a point in that domain, the KLI space. Right, that's my domain. Now what happens to it? Well, it goes into this g function, and then out comes some point in R2 with variables r and p. So r and p axes, and so the output will be, maybe some point there. And so what does this function do? Well, the function, a representation of some of what this function does is it takes that point to that point. Now, it's not a great visual aid either, right? Let me pick on my own picture here. I can only see a very, very, very small amount of what G is doing here. I can see what G is doing at just at one point. And that's not good, right? That certainly leaves something to be desired, I'll say that, right? But it's better than nothing. Got to give me that, right? Because if you stick to graphs, you've got nothing. This is something. That's a win. Okay. I'm going to further point out that, in fact, this is a really, really natural way to understand multivariable functions, and also a really valuable way to understand multivariable functions. One thing that we're going to be thinking about, and this is just foreshadowing, but I think it's useful to do the foreshadowing. Hopefully no surprise, but sometimes we're going to want to know, hey, if I move that input, if I change the input to this function a little bit, how does the output change? And notice, even though I can't draw the whole of what G does, I can actually represent the idea of, from this point in the domain, maybe moving by some amount in the domain, and I can reasonably ask, okay, correspondingly, if I do move like that in the domain, well, what is the corresponding movement in the target? And so you can see, I mean, again, this is one of the fundamental questions of calculus. How do input changes become output changes? Right? Think about that. That's what a derivative is, if you really think about it. More on this later. This is, again, just foreshadowing. But derivatives are a way of saying, if I change my input a little bit, how much is my output going to change? Here I have a picture after a fashion, right, of what a derivative really kind of is in a multivariable context. Again, way better than a graph, which we can't draw at all, not even a little bit. Okay, so this is what a graph is. I'm for them, not against them, but I do want to point out that it is a tragic error that students routinely make in multivariable calculus classes, which is to just 100% go all in on graphs and say, you know what, I don't need these other ways to visualize functions. I like graphs. I remember graphs. I'm accustomed to graphs. I'm a graph kind of person. Right? Big mistake. Big mistake. You can't get through a class like this with that point of view. So, anyway, heads up. I've been doing a lot of talking. Let me pause here for a second. Anybody have any questions? How we doing? Everybody happy? Okay. All right. Here's a different kind of picture. Something called a level set. Also flawed. Also very useful in some contexts. Conveniently useful very often in different contexts than when graphs are useful. Or where this other, and I'm not even sure what to call it. Sometimes I call this the natural picture of a function. Because, again, domain, there it is. Right? Target, there it is. It is actually a pretty darn natural way to understand functions. So, compared to the natural picture of a function or the graph picture of a function, level sets fill in a nice little gap in a useful way. So here's the definition. Given a function from Rn to R1, a level set of that function is the set of solutions to that equation. You just take the values of the function and set them equal to a constant. By contrast, graphs do not do that. Graphs take the function. They don't set the function equal to a constant. You set the function equal to a new variable that then becomes a coordinate in this now n plus 1 dimensional picture. So this is very, very different, right, what we're doing here. Okay. Notice, let's count variables. How many variables do we see in this equation here? Well, all the variables are right there. There are variables in the domain. This is an equation in the domain. Therefore, the level set lives in the domain. Kind of natural, right? Graphs don't have that feature. Graphs live in weirdo world that we just made up for its own purpose. Level sets live in the domain. Here's an example for relatability. Anybody who's ever gone hiking or thought about going hiking or something like that, you may have seen a map that has what they call contour lines. Contour lines are, they draw lines, curves, right, where each curve represent points at a given altitude. And, you draw enough of these things, you draw enough of these contour lines, and you can kind of get a sort of a vibe, a sort of a sense of what the mountain looks like, right? I mean, you probably have some sense of what this mountain looks like here. This has certain purposes. You can see, if you're really looking for a challenge, you could try to go up that way, but you're going to climb the whole mountain over a very short distance. Whereas, if you don't want that kind of challenge, then maybe go up that way. And there's a lot of distance that you're covering to gain the exact same amount of altitude. So that's going to be a more pleasant hike, right? This is what I'm doing these days anyway. So it's got some value, right? You can get some geometric sense of what the function looks like from that picture. So contour lines, very natural, and I'll point out that they are a level set. Right? Contour lines are level sets of the altitude function. Let's think about how altitude near this mountain is a function. Well, you give me a location, right? And there's some function that tells me, well, what's the altitude at that location? Notice I don't have anything to put on the picture to represent that altitude because it's not that kind of a picture, right? It's not a graph. The value of the function is not like vertical distance at this point. This is just the domain. There is no picture here of the output variable. There is no output variable axis on this picture. Okay. Right. So it's a level set. Everybody okay with that? If you've never done any hiking and have never seen these pictures and have no idea what I'm talking about, if you've ever watched the weather, or I don't know what the internet does with weather these days. When I grew up, there used to be this thing called the weather on the news. The news, let me rewind. The news was this thing on television. They still have television, I'm pretty sure. Right? But then there'd be the news. It would come on at 5:30, and everybody goes and watches, because otherwise you wouldn't have any idea what's going on in the world. So there was no Twitter. There was no CNN, right? So anyway, they would put these pictures up. Let me make a better color choice here. They'd have this is the screen, right? And they would draw a picture of, I'm not going to try to draw the United States or North Carolina or what have you, but then they would draw these lines like that, and then they would color code, and it'd be, it's real hot down here, so they'd color that red, and then it would be still pretty warm, but not quite as warm over here in this zone, right? And then maybe a little cooler in this region here, and then maybe just downright comfortable over here, perhaps. Right? And so you see pictures like this, and then if you know where you are, you have some sense of, okay, I'm going to be a little bit warm if I'm here, or I'm going to be a little bit hot if I'm there. Right? So anyway, this is another kind of a picture of something pretty relatable, and I'll point out again, these are level sets. Now, the way they would do this in the old days, I don't know how they do it now, is maybe they'd say that this is the 80s, and this is the 90s, and this is the 100s. I'm from Houston, so I saw a lot of that. These are the 70s. Well, if you think about it then, what that means is that this curve right here, that curve is where the temperature is right on the border between the 70s and the 80s. That means that temperature as a function of longitude to latitude is 80. That is therefore a level set. See, I'm setting it equal to a constant. That is a level set of the temperature function. Yeah? Everybody on board? And then likewise, this is where temperature is equal to 90, and this is where temperature is equal to 100. So another real world relatable example of level sets. Okay. So it's a different kind of a picture. Different sort of geometric intuition. Pros and cons. We'll talk about some of those as we go along. I will point out there is a connection. There's a relationship between graphs and level sets. It actually motivates the term level set. Let me just remind you the way we make a graph. The way we make a graph is we take the function, the values of the function, and we set them equal to a new variable. So maybe z. By the way, don't inadvertently choose for your new output value variable a variable that you've already got as an input variable. So don't say y equals f of x comma y. So you're confusing your variables there. Okay, so that's how you make a graph. We've talked a long time ago about that if you have a graph, the way you can take a cross-section of the graph is to further require the equation of a plane. A horizontal plane if you want to have it be a horizontal cross-section. So z equals c. And then just notice what we have here then is that, in fact, if you set f equal to z, but then z equal to c, you're between the two of those, you are in effect setting f equal to c, which is a level set. So the punchline here, this little clever observation, is that horizontal cross-sections of graphs are level sets. Yeah. And you might even say, instead of horizontal cross-sections, you might even say a level cross-section of a graph. And I think that motivates the name. You might think of horizontal as being level. Anyway, whatever. So neat observation. Let me show you an example. Let's get our hands dirty. Here's a function. Notice a function from R2 to R1. Because we have two input variables, we have one output variable with a formula for it there. So this function, let's talk about its level sets. Reminder, how do we make level sets? Well, we take the values of the function and we set them equal to constants. Right? That's what a level set is. Set the function equal to a constant or several constants. Each constant you choose, of course, you get a different curve. So different values of c give you different curves. Okay, so those are level sets. Let's talk about the graph of this function. Now, same function, I emphasize, same function. What is a graph? A graph is what you get when you set the value of the function equal to a new variable, not a constant. Give me 2 seconds. Not a constant. Notice then we have that, very importantly, a different equation. That equation of the graph is importantly different from that equation of a level set. I mean, they're just totally different. The one up there only has 2 variables, for crying out loud. This one's got 3 variables. These equations live in different worlds from each other, very, very different. And yet, notice, if I take, and by the way, recognize this graph, green. This graph, we've already studied that equation, right? Y'all remember, this is one of the ones we did when we were talking about rotations, z is x squared plus y squared. We know that graph is that. Notice, as described on the previous page, if I take a horizontal cross-section of that graph, I get a circle which looks an awful lot like that level set. Yes, sorry.
So I was going to ask you, if we want a level set that looks somewhat like that one, that's like representative of the shape of the,
yeah.
How do we decide the constants and the spaces?
No, that's a great question. So all of these kinds of pictures, when we're drawing pictures of multivariable functions, there is no perfection, because we just don't have enough dimensions, right? So any kind of a picture we're going to draw is going to have a bummer downside about it, and you've just put your finger on exactly one of the bummers about level sets. How many different level sets does this function have? Well, it has infinitely many level sets. because this could be any constant. There's infinitely many of them. So if you really want to draw all of the level sets, if you think about it, all you're going to get is just get a piece of black construction paper. Right? It's kind of goofy, but a solid black is what the collection of all the level sets would look like. And it's just not helpful, right? So you kind of have to make a sort of a kind of an artistic choice of, which level set. It depends on the function. Which level sets are going to kind of communicate the most about what the function does. Graphs of single variable functions have spoiled us, right? Single variable graphs are awesome because, look, that tells me everything about what that function does, right? To my ability to draw. It does anyway. Let me point out, though, that graphs in this, a lot of people would say, oh, well, same for this graph. This graph shows everything. And I point out that, no, it doesn't. This graph is a scam, right? You think I've drawn a surface? No, I haven't drawn a surface. I fooled you. I drew a couple of lines. And now I've tricked your brain into thinking that you're seeing a surface, but you're not seeing anything right there. Anything that you think you're seeing in there is your imagination. See what I'm saying? Right? So, that's a really awkward fact about drawing surfaces in 3 dimensions. You're not really drawing them. Pencils make lines. That's just how they work, right? So, if I wanted to really make in fact, true graph of this function, I would have to actually sculpt something in 3 dimensions. And it's just not feasible most of the time. So, yeah, so to your question, any kind of a picture that you draw of a multivariable function is going to have a major shortcoming of some sort, yeah.
In the previous question, if you changed the domain space to R3, would this change? Oh
yeah, no, that's right. So I'm going to interrupt and put that on hold because that's a punchline for me a little bit later on. Yeah, it's a great question, but I'm going to delay. Yeah. Okay. Yes.
Wait. So could you have a level set of a plane?
So, okay. Thank you for that question. Error of type. So, a plane is not a function. See what I'm saying? So functions are an algebraic object. They're this, a lot of people think of them as a black box, but a function is a particular type of algebraic critter where stuff goes in and then stuff comes out. It's not what a plane is. A plane is a geometric object, right? Now, you could say that a plane is described by an equation, but I emphasize an equation is not a function either, right? An equation is a statement, or we described it previously as a test. It's not a black box that's where stuff goes in and stuff comes out. So, yes, you can't really talk about level set of a plane because, it's the wrong kind of thing, right? You can't talk about level set of a bicycle either. It's equally sort of like it's a disconnect. Yeah. But I totally see where you're coming from. And we're going to talk about examples that relate to that kind of thing. But so the big takeaway I wanted you all to get from this question, can you talk about a level set of a plane is how easy it is to inadvertently be a little sloppy. I'm sorry, I don't mean to pick on you, but a little bit error of type prone in talking about these kinds of things. And it's going to turn out to be that errors of type and that little bit of sloppiness is going to have catastrophic consequences if we're not careful later on. So I'm going to totally address these kinds of things as we go on through the next few pages. Yeah.
Why can't we imagine for a plane? Why can't we imagine that there are going to be infinitely many lines stacked one upon the other?
Sure.
If we try to draw this kind of a graph.
Still not a function.
Yeah, but we could still draw this kind of a graph, but just be one line.
I guess I'm not following. So, what are you trying to do?
If we draw level sets for a plane, can we not make it?
Well, see, again, error of type. What you just said doesn't make sense. You can't talk about. There is no such thing. It's not that we can't draw it. It's that it's a meaningless concept. Level set of a plane just doesn't make sense. Notice level set. If you go back to our definition of a level set, you can talk about level sets of a function. Right? You need to have a function to go through this process of taking the values of the function and setting them equal to a constant. A plane is not a function. right? And now there's a tendency to say, okay, well, yeah, but come on, but look, a plane, come on, it's described by a function. Which function and in what way, right? So I've got another example coming up that I think is going to clarify the complaint that I'm making. I know it seems like I'm being super quibbly right now, but what I'm trying to do is we are actually in a dangerous minefield of oopses, and it's important that we see where the landmines are here.
N has a constraint there.
I'm sorry?
N has a constraint out there where you describe Rn to R1.
Well,
N should be greater than 3.
Oh, no. N could be anything. So we've already seen an example here. Here are level sets of a function from R2 to R1, yeah. It tends to be a little useless. I mean, you could talk about a function from R1 to R1 and what are its level sets, and they tend to be super boring. So in some contexts, level sets are just not such a useful construction, and in some contexts they are. So, yeah, I mean, we'll see various versions of it. Okay, so let's talk about this plane here. This actually kind of gets to the questions y'all were asking. Here's a plane. Okay, let me be a little bit more careful on that. The plane is a geometric thing. This is the equation of that plane. Okay, but let's ask the next question, though. What function? What's the function here? Is there more than one function that relates to this plane? And in fact, there's a couple of them. There's actually kind of 3 of them, depending on how you think about it. So what functions can we think of? Well, the first question I can ask is this plane a graph of some function? Surely if I could produce a function whose graph is this plane, then you got to give me that function matters to this plane, right? There's natural connection to this plane. So, let's be careful here. And again, the devil's in the details. There's a dangerous minefield that we're walking around in here. What do we mean by graph? A graph, that's what you get when you take some function of something and you set it equal to a new variable, right? So graph means we're setting it equal to a new variable. If I want the graph described by this equation, if I want the graph to describe the same equation that I've already got to describe this plane, what variable am I going to stick over here? What variable is some function equal to? And the way this equation here is written, none. There's no variable as it's currently written that is that. But notice I could ask, can I take this equation and write it equivalently? Can I solve for one of the variables? Perfectly legal, doesn't change a thing. You just manipulate an equation around, right? Easy answer to that question is, yeah, I can solve for z. Right? I could take this z, solve for it, and what you will find you get is this function. That's the function which, if you set it equal to z, gives you that equation describing the plane. Let me say that differently. That's the function whose graph, strictly interpreted, right? Be super careful. Don't use graph interchangeably with other things, right? This is the function whose graph is this plane. Yeah, is everybody on board? And just to be a little bit more blunt about it, check it out. If I were to take this function and set it equal to a new variable, I emphasize that's what a graph is, right? This equation is exactly equivalent to that equation. They have exact same solutions. I just move stuff around. Okay. On the other hand, now, is this the only function that we can talk about that relates to this plane? No, not at all. It's also a level set of this other function here, right? So this function here, which leaps off the page at you, right? That's a function for which a level set gives you the plane. Yeah? So this is the danger I'd like to point out in, being a little too fast and loose of conflating geometric objects with the functions that, that they describe in one way or another. Is that the one way or another makes for lots of, you got to be careful of what do you mean, right? So both of these functions in their own ways describe this plane. So here's the problem that we're going to face, and I've seen this happen a million times over the many years I've been teaching this class, that students are a little too sort of like, come on, look, it's just, isn't this Algebra 1? I thought I was beyond that, right? We'll then try to understand something geometric about the plane using calculus. No surprise, we do that with, think about it in single variable calculus classes. You determine the slope of a tangent line to a curve by doing an algebraic construction called a derivative, right? And so you can determine geometric information about a geometric object by doing calculus on the corresponding function. Well, you'd better know which function should you be doing calculus on, right? So what I'm going to loosely call the calculus of graphs. It's very useful. There's certain kind of calculus you can do and make interpretations from that calculus about geometric features of the graph. But there is also a calculus of level sets. There's calculus that you can do and write down which will allow you to draw geometric conclusions not about the graph but about the level set. So if you're going to use the calculus of level sets, you'd better use the function whose level set describes the object you're interested in. If you use the calculus of graphs on that function, you're going to get a catastrophically wrong and possibly meaningless answer. And again, I've seen this a million times, and especially in the old days when I was first teaching this class, before I started making a huge deal out of this like I am now, right? Students kind of went through the whole course always being kind of like mystified by, well, why do I keep getting wrong answers? Because I keep doing calculus and I keep applying it to the shape, and yet half the time it seems I get the wrong answer. It's because they're not being careful about the distinction. I saw a hand back there somewhere a second ago. Is it okay? So I guess that's good. Okay, so heads up. Here's another example. Let's look at this line. Here's a trivial line. Right? Flashback to Algebra 1. There's the equation of a line, yawn, boring, middle school. Right? Okay, but wait a second. Notice this line can be described in different ways by each of these three very different functions. Right? This same line is the graph of that function. It's a level set of that function. And it is parameterized by that function. Now, there's a flashback to parameterizations that we talked about last week at some point, I think it was. Three totally different functions. Really, they're not just different formulas. They have different domains and targets, right? This function here is a function from R1 to R2. This is from R2 to R1. This is from R1 to R1. They're fundamentally different functions. So if you want to understand this line, if you're going to use calculus to do that, you better make sure you are entirely clear on what kind of calculus are you using, and don't apply level set calculus to a parameterization or parameterization calculus to a graph or whatever mismatch along those lines. Okay, all right. Oh, I guess while I'm here, before I go on, you'll notice very quickly on my old exams that there's a bunch of questions that are kind of like this example. I use the question a lot because, I just want to make sure students get the message that this is important, right? I want to make sure students practice this. And if that makes me a little predictable, I think it's worth it, right? So the question takes the form of, hey, here's a line, or here's a curve, or here's a surface, what have you. And I'll say, for what function is this the graph? And for what function is this a level set? And, for what, give me an example of a function that parameterizes. Right? Those kinds of questions. And it happens super, super often that even though the algebra here, I mean, look at the level of the algebra, right? Nothing's even quadratic. This is the actual mechanics of the algebra of doing these kinds of problems is like easy algebra 1 level algebra. There's no tricky curves on the algebra, right? What makes these questions challenging and what's important to the grading of these questions is our students strictly and correctly interpreting what these words mean, how those constructions work, and do they actually get the right answer? And if I ask for, this is the graph of what function, and if you give me this function, I'm not going to be given any partial credit for that. That's, the fact that, all I did was label it wrong, that was the only, you had one job in some sense, right? That's the only thing you have to do on these. The algebra is trivial, right? So make sure that you're careful about this. And let me point out one other thing. This is a little pet peeve of mine, but this happens a lot. Students will sometimes write, L is I'm going to edit what I have here to represent, so I'm going to disavow this momentarily, but students will write L is the graph of 6 minus 2x over 3 equals y. This answer is really importantly wrong. L is not the graph of an equation. L is the graph of a function. This equation describes the graph, right? You can't say graph of a graph. Is what the student has written here is morally saying L is the graph of a graph, and that doesn't make sense, right? So keep in mind, graph is a word that says you give me a function, out comes an equation describing a geometric object. So this is another sort of like, I'm going to call it a little bit of a sloppiness, a misunderstanding of the meaning of the words, right? Carelessness of the terms. So make sure you don't do this. Now let me put a big X through that again to emphasize that I'm arguing against this, not for it. Right. Just in case anyone's watching my video on mute, for example. Okay. All right. So yeah, just this is what I'm looking for. Please don't append, for good measure equals y. That's wrong. Okay. So a couple of quickie observations, and I know I only have 2.5 minutes left. You'd be surprised how fast we can go through the next couple of pages, though. Neat fact about level sets: every graph is a level set. That's really neat. Every graph is a level set. Now, I emphasize, of a different function. Obviously, a graph of a function is not the same as a level set of that same function. That's obviously not true. But check it out. If you have a graph, right, here's a graph. That's what a graph is. I said a function equal to another variable. There's a graph. Well, I can very easily just adjust that equation around a little bit. And I hardly did anything to the equation. I just moved one term over to the other side. And notice what I now have is, instead of something written as a graph, I now have something written as a level set. Yeah, got something equal to a constant. Now, this something that I'm setting equal to a constant, this thing whose level set I'm talking about, that is now a new function. That's not the same function, f. This has got an extra bit of junk in it. This is y minus f. It's different. It's got a new variable in it, right? The formula for f, there's no y's in the formula for f. This expression here has a y in it. Importantly different function. I'm going to give it a different name. Call it g. Right? But g's zero level set and f's graph are the exact same equation, exact same object. So a relatable example, I think, is go back to this function that we're very familiar with. This function here, its graph is equivalent to this function here's level set, as evidenced by the fact that, well, these two equations here are totally equivalent. Okay, so neat trick. Where this is going to come up is that sometimes you'll find yourself looking at a graph. Maybe you're given the function whose graph is the object. So you're interested in this paraboloid. We know that's a paraboloid surface. It may be that what you've been asked to find, you're like, wow, the calculus of level sets would totally allow me to get what I'm looking for. And then you're like, oh, but I don't have it written as a level set. I have it written as a graph. I can't apply the calculus of level sets to a graph. That's bonkers, right? But so this trick allows you to take something given as a graph and reinterpret it as a level set. And so then to this function, you can apply the calculus of level sets. So it's a really useful trick. Do notice it does not go the other way. Not every level set, for example, here's one. Not every level set's a graph. This level set fails the vertical line test, right? So massive failure of the vertical line test. So this is not a graph. So this is what I would call a superiority of level sets in a way. You can always convert any equation, in fact, to writing it as a level set. Level set calculus is arguably more versatile than graph calculus. None of which we've seen yet, I know, right? We'll get to the calculus later. And I'm out of time. So we'll pick up here on Wednesday. See y'all later.